Hello everyone, this is Naga Lakshmi Devi, Assistant Professor, Department of Freshman Engineering, IARE, Hyderabad, Telangana. Now the topic is limit of a functions. Examples. The limit of a function example is find real and imaginary part of f of z equal to z square plus 2. Now let f of z equal to z square plus 2 is the first function. Here always the z equal to x plus iy. X plus iy. Now x plus y iy whole square plus and another z is there. Here z equal to x plus iy. Then we get, that is the solution. X plus iy whole square, that is x square plus I square y square. I square is nothing but, here I square is nothing but minus 1. Now substituting that term, we get it minus y square. Then remaining is 2xi y plus remaining x plus iy. Now here imaginary parts are one side and remaining parts are real parts are in this one. Here x square minus y square plus x is a real part and I into 2xy plus y is the imaginary part. Therefore, u of x equal to, here u of x equal to x square minus y square minus plus x, and v is 2xy plus y. This is the limit of a function. Earlier class we discussed about the limit of a function. Now this is the example. Real part is x square minus y square plus x and imaginary part is 2xy plus y. Now this is the, here f bar of z is not equal to f of z bar. Next, continuity of a complex function. A function w equal to f of z is said to be continuous at z equal to z naught if the limit of a function is limit z tends to z naught, f of z equal to f of z naught. Here earlier in limit of a function or complex function, always the domain is here. Now the range is this one. Domain to range coming from this one. Then w equal to f of z. Domain of range of. Okay, this is z plane function. This is w plane function. W equal to f of z. The function of z involved here. Then limit of a function is limit z tends to z naught equal to into f of z equal to f of z naught. We observe that for the function f of z to be continuous at z naught, the function must be defined in the some neighborhood of the limit of a function. It is included by the z naught, and the limit is same. Limit z tends to z naught, f of z equal to f of z equal to f of z naught. Now this is the complex. That is the continuous of a complex function. Now derivative of the complex function. Let f of z be the single valued function of the variable z equal to x plus iy. Here x plus iy is the differentiable function of f of z. Then the derivative of w equal to f of z is defined to be the derivative of this one. This one here, w is the derivative function and f of z is a function. Then dw by dz equal to f dash of z equal to limit z tends to delta z tends to 0 into f of z plus delta z minus f of z by delta z. Here delta z sometimes we are writing as like this also. Now that is the derivative of the function, provided the limit exists and it the same value for the different values in which delta z. It is approaches by the 0. Now problem. The first problem of using the different definition of the derivative. Find the derivative of the f of z square for all z. That means here f of z equal to z square. Now f of z equal to z square. Here what about z? F of z equal to z square. That means z equal, already we know, z equal to x plus iy. Iy whole square. That means x square plus y square into minus 1. I square is nothing but, since I square is nothing but minus 1. Substituting that one plus 2xyi. Now that is the function. That is the explanation of the function f of z equal to f dash of z. Now substituting here, that is f of z equal to f of z of Z is already, it is Z plus delta Z minus f of Z equal to here x square plus y square plus 2xy by delta Z. Then substituting that one here, Z and Z square will be cancelled. The remaining we get the final solution. Now substituting each and every term here, we get the same function. Now f of Z equal to, that means Z plus delta Z whole square minus f of Z means Z square by delta Z, that equal to Z square plus delta Z square minus 2Z delta Z minus Z square cancel into delta Z. Now common with the delta Z, that is delta Z minus 2Z by delta Z. Now delta Z cancel. Now applying the limit here. Limit delta Z tends to 0 into delta Z minus 2Z, that equal to, applying here it is, we get only minus 2Z. Here a plus b whole square, no? That is here it is plus, this one plus. Maybe if it is delta Z not equal to 0, if it is the values, it is 2Z is the final solution. The final solution is 2Z. Now that is the function of the derivative of the given function here, Z square. Now similarly, we are solving this one also. Now here it is, here I am substituting Z, f of Z is equal to f of Z plus delta Z minus f of Z. Here f of Z cube means here Z plus delta Z whole cube minus 2Z, and another one is f of Z equal to Z cube minus 2Z. Overall this one. Now that is expansion of that one, and another one is Z delta Z. Here total it is Z cube plus 3Z square. By applying Pascal formula 1 here it is the 2. Now this is also 3, this is 3. That means 3Z square delta Z plus 3Z delta Z square plus delta Z square minus 2Z whole cube, that equal to 8Z cube minus Z cube minus 2Z by delta Z. Now Z cube cancel. Now remaining 3Z square, and overall in the each and every term it is delta Z is there. Common with that term, that is 3Z square plus 3Z plus delta Z minus 8Z cube minus 2Z by delta Z. Delta Z cancel. Now simply applying the delta Z tends to 0. Here we get the 3Z square. Now here it is delta Z term 0, and remaining is 3Z square, and it is 3Z overall. 3Z, this is Z. Overall this is also cancelled, minus Z. This one is minus Z. Total we get only 3Z square minus 2. This is the solution. Now another part is Z equal to 1. Here Z, we are substituting Z equal to 1 in this condition, that is 3 minus 2, we get 1. That is the final solution of the second part. Now the analytic function. Now the analytic function is a complex function is said to be analytic on a region R if it is complex differentiable at every point in R. The terms holomorphic function, differentiable function, and complex differentiable function are sometimes used interchangeably with the analytic function. There are totally 3 types of analytic functions are there. Now here if the complex function is analytic on a region R, it is infinitely differentiable on R. And singularity property is the first one. Next one CI equations, and another one is harmonic motion. Then first one is a complex function may fail to be analytic at 1 or more points. It may be fails on 1 or more points. At least 1 point it will be fail. It is not analytic. That's all. And the point to the Presence of the singularities are long lines or line segments through the presence of the branch cuts. For example, f of z equal to 1 by z is analytic everywhere except at z equal to 0. Why? Because if I am considering z equal to 0, since here z equal to 0 means 1 by 0, that is infinity. It is not an analytic. Analytic, for example, it is analytic means the line along with the parallel paths or some perpendicular paths or some along with the cycle or something. It is infinity means there is no extensions, nothing is there. That's why it is not an analytic in this condition, 1 by z condition. At z equal to 0, and the point is z equal to 0, it is not an exist, then that z equal to 0 is isolated at a singular point. Then it is called a singular point. If it is analytic, then it is called singular point. Next one. Next method is cautious cautious Riemann equations, otherwise CR equations. The theorem: if necessary and sufficient conditions for the derivative of the function w equal to u of x comma y plus I into v of x comma y equal to f of z to exist for all values of z in a region R is called, for the first function is, the first condition is dou u by dou x comma dou u by dou y comma dou v by dou x comma dou v by dou r are continuous functions of x and y in R. Then the condition is dou u by dou x comma dou u by dou x equal to dou v by dou y comma dou u by dou y equal to minus of dou v by dou x. Then it is called CI equations are satisfied. For example, you are considering any function z square. That is, z is nothing but x plus iy. That is x plus I square, I square. X square minus y square plus 2xiy. Now, here is a real part is x square minus y square. That is nothing but u. Here always they are talking about the u and v. That's why it is u. And v equal to 2xy. Z square equal to, I am choosing x plus, here it is fixed with x plus iy whole square. Then it is x square minus y square plus 2xiy. Then u equal to, here the real part is x square minus y square and v equal to 2xy. The z equal to, here w equal to u plus iv. That is w equal to x square minus y square plus I into 2xy. Now differentiation, that is u equal to dou u by dou x. Differentiation part is x square derivative is 2x. Y square treated as a constant. In partial differentiation, y square treated as a, here it is constant. Then dou v by dou y. Dou v is this one. Now with respect to y means y is 1, 2x is constant. Next, dou u by dou y. That is 2y. And dou v by dou x. That is minus dou xy. That is 2y. That is minus 2y. Therefore dou u by dou x equal to dou v by dou y. Then this is dou u by dou y. Both are same, minus. Here x square minus y square is there. That's why dou u by dou y equal to that one. Now it is dou u by dou v. Next dou v by dou y. Both are 2x. Then it is equal. Next one, dou u by dou y equal to minus dou v by dou x. Now both are is minus 2y. Then it is also same. Then it is CI equation satisfied. This is the example of the CI equation. Now these two relations are known as the Cauchy-Riemann integration, in briefly CI equations. Cauchy-Riemann integration equations are CI equations. Both are same. If both the two conditions are satisfied, then it is CI equation. Otherwise, it is not CI equation. That is not an analytic solution. Now the proof of that condition, that property. First one, I am choosing the necessary condition. That is, let w equal to u of x comma y plus I into v of x comma y, that equal to f of z be a single valued function. F of z is single valued function of the variable z equal to x plus iy. Let delta u and delta v be the two small increments of u and v respectively. Here the corresponding to the increments delta x and delta y of x and y, so that delta z equal to delta x plus I delta y. Here z equal to x plus iy. Now the delta z equal to delta x plus delta iy. Now let f of z is possesses a unique derivative at any point p of z, then the limit f dash of z equal to limit z tends to delta z tends to 0 f of z plus delta z minus f of z by delta z. That is derivative of the complex functions. Now that is a unique point value. Now it will be converted into in terms of uv. Okay, that is limited delta z tends to 0 u plus delta u plus I into v plus delta v minus f of z is nothing but u plus iv by delta z. Now substituting that one, finally we get delta u plus I delta v by delta z. Here u plus iv is z. This is z. All are cancelled. Only we get only delta u plus delta v. That is, for example, u plus delta u plus iv plus I delta v minus of u plus delta v can be written as z. We are choosing like that. Next, u plus iv is z plus delta u plus I delta v minus z. Both are cancelled. Remaining delta u plus I delta v. I am writing here that one by delta z in denominator part. Now next. Now it is splitting into two parts. Delta u by delta z plus I into delta v by delta z. That is the next expansion. Now since delta z can be approached as 0 in any manner, we can first assume delta z to be the wholly real and then wholly imaginary. It is imaginary part or real part. In earlier it is delta u by delta v is the delta v delta u. Delta u is a real part and delta v is the imaginary part. Now here delta z is, we are thinking in real, then delta y is 0. Then only we get delta z equal to delta x. Maybe it is, we are thinking in real part, delta x is 0. That is delta z equal to I delta y. Now the final expansion is f dash of z equal to limit delta x tends to 0, delta u by delta x plus I into delta y by delta x. Then the finally we writing as delta u by delta x plus dou u by dou x plus I into dou v by dou x. Delta in terms of limits we are applying that one, we get partial derivatives. This is the dou u by dou x plus I into dou v by dou x. Similarly, we are applying in sufficient condition, we get another one. That is imaginary part. I am explained in earlier. When delta z is imaginary, that is the condition. Then delta x equal to 0 and delta z equal to I delta y. Now we get dou u by the final solution, dou u by dou y into y I plus dou v by dou y equal to dou v by dou y minus I into dou u by dou y. Now equation 1 and 2, equating that both at a time, we get the dou u by dou x plus I into dou v by dou x equal to dou v by dou y equal to minus I into dou u by dou y. Now equating the each and real and imaginary parts, we get this is the real part and this is real part. That is dou u by dou x equal to dou v by dou y. That is the first condition. CI equation second property. Second property first condition. And another condition is I into dou v by dou x equal to minus I into dou u by dou y. Now I we get cancelled. We get only dou v by dou x equal to dou u by dou y. This is the second condition of the CI equation. Second condition, second part. Now these are the CI condition satisfactions. Proof, theorem proof. That is the final condition. Dou u by dou x equal to dou v by dou y, comma dou v by dou x equal to minus dou u by dou y. That is the CI equation satisfied. Now the condition is sufficient condition. Necessary condition is completed. We have condition w equal to f of u plus I into f of v. We are choosing that one. We get dou u by dou x like that. Now we are condition. We are taking reverse order. That is dou u by dou x equal to dou u by dou v by dou y. That condition we get w equal to u plus iv condition. Let f of z be a single valued function possessing a partial derivatives dou u by dou x into dou u by dou y into dou v by dou x, dou v by dou y. Then it is satisfied at each point of the region in the CI equation. Now equation above equation 3 satisfied. Then it is called by applying the Taylor's theorem. We get two individual variables. That is First one, f of z plus delta z equal to u into x plus delta z comma y plus delta y. That means it is, we are considering in x-axis, y-axis, the x variables are x plus delta x, next delta x, next x plus 2 delta x, continuing this process. Similarly, y also, y plus delta y plus delta y plus 2 delta y, like that. Now continuing this process, we get the equations. F of z plus dou u by dou x plus I into dou v by dou x into delta x plus dou u by dou y plus I into dou v by dou y into delta y. Now omitting the terms of the first powers of delta x and delta y, we get the f of z equal to this one, dou u by dou x plus I into dou u by dou x. Now by using the Cauchy's equation, now equation 10 can be replaced by dou u by dou y equal to dou v by dou y, and similarly by minus dou v by dou x equal to dou u by dou x respectively. Now then f of z plus delta z minus f of z equal to same above equation. Then equating each and every term, then f dash of z equal to, now here it is derivative part of the left hand side. This is a real part of the derivative part and this is imaginary part of the right hand time. Now the total you can be written as x plus iy equal to fz. Similarly, delta x plus delta iy is nothing but delta z. Then we get that is nothing but f dash of z. Now the limit delta z tends to 0, f of z plus delta z minus f of z by delta z. This is the final one. This is the differentiation part of CR equation. This is sufficient condition part. Already necessary condition is satisfied. Now sufficient condition also satisfied. Then both are same. Then it is called a necessary. Then it is CR condition. CR theorem is satisfied. CR theorem is satisfied. Now analytic function of the conjugate function. That is the third method. Is called a conjugate properties. Now example of the non-analytic, already analytic condition satisfied, that is z squared property is completed. Now non-analytic condition, if w equal to log z, that means z equal to x plus iy, substituting z equal to w equal to log of x plus iy. Okay, find f of z and determine where f of z is non-analytic. Solution, we have f of w equal to f of z, that f of z equal to u plus iv, u in of x comma y plus iv of x comma y, then log of x plus y. Already here log z is there, log z is nothing but x plus iy. Then 1 by 2, now derivative of this one, 1 by 2 log of x square, that means derivative of log of x plus iy equal to 1 by 2 into log of x plus x square plus y square plus I into tan inverse of y by x. Now substituting that one, we get here, show that u equal to 1 by 2 log of x square plus y square, v equal to in terms of I part, that is tan inverse of y by x. Now here dou u by dou x equal to 1 by 2 log of, means here x square 2x by x square plus y square, the derivative of u, this derivative of u equal to 1 by 2 is a constant, remaining part is this one. Now log x derivative is derivative of log x equal to 1 by x. Here x means x square plus y square. Now what about x square derivative? That is 2x. Substituting that one, 2 get cancelled, remaining x by x square plus y square. Next dou u by dou y, 1 by 2 into same dou 2y, y square derivative is 2y. Now 2 cancel, we get y by x square plus y square. Already we know earlier, that is in any region polar coordinates of x equal to r cos theta, y equal to r sin theta, so that x square plus y square equal to, x square means r square cos square theta, and y square means plus r square sin square theta. Now r square common, that cos square plus sin square theta equal to 1. Then x square plus y square equal to r square. Then r equal to square root of x square plus y square, and theta equal to tan inverse of y by x. Here this one is nothing but r, this one is nothing but theta. Now the another condition is dou v by dou x. Dou v by dou x, here v equal to earlier we know what is v? V equal to tan inverse of y by x. Now tan inverse y by x means it is 1 minus 1 by minus y by x square plus y square. And dou v by, with respect to, I am choosing here x. Tan inverse of y by x. That's why minus y. X derivative is 1. Now here dv by dou v by dou y. Now the x by y square plus x square. Here y square 1 by, here tan inverse of x, tan inverse of y by x. Tan inverse of y by x. Now differentiating with respect to x means here minus, this is y as a constant, y into 1 by x derivative is minus 1 by x square. Now numerator is x square is there, then these both are cancelled, we get in tan inverse x means x square by x square plus y square, x square cancel, minus y by x square cancel, we get minus y by x square. Next, tan inverse of y by x with respect to y. With respect to y, that means here also same, x square by x square plus y square into minus y. Y is nothing but 1 by x. Both are x cancel, x square cancel, x by x square plus y square is, we get the answer. This is the part of dou v by dou y. Now dou u by dou x equal to dou v by dou y, and dou u by dou y equal to minus dou v by dou x. Since here all are not equal, here dou w by dou z, here since the CR equations are satisfied and the partial derivatives are continuous, expect at 0, 0. Why? Because here denominator 0 means the total equations are infinity. Hence W is the analytic everywhere except at z equal to 0. Any at least one point is in undefined, then it is not analytic. In the region, it is one region is there. In outside the region, number of points are there. At least one point is not in inside the region or outside the region, not in boundary value. That is the final value. Not in the boundary value, then that is not an analytic. Then here one point is not analytic, that is z equal to 0. That point is not analytic. That means total is not an analytic. We can see that one also. dw by dz equal to dou u by dou x plus I into dou v by dou x equal to, overall the condition is this one. That is nothing but else. Now LCM with denominator x square plus y square, that one can be written as x square x plus iy plus x plus I minus y. Then x plus x minus iy is there. Total numerator denominator get cancelled. The remaining is 1 by x plus iy, that equal to 1 by z. Then z not equal to 0 condition compulsory. Similarly, here one condition is not satisfied, then it is not an analytic. Now the question is not, we can proof of the not analytic. It is not an analytic. It is not satisfied with the CI equation. Then it is not a Cauchy-Riemann equation. It is not analytic. Next, another example. Here also another examples are there. Prove that the function f of z is defined by f of z equal to x cube of 1 plus I minus y cube into 1 minus I by x square plus y square. Z not equal to 0. Here 0, otherwise 0, z equal to 0. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.